Somewhere in your city tonight there is a building that is almost entirely still. The offices are empty. The hallways are dark except for the faint amber glow of exit signs near the stairwells. The elevators are resting on their home floors. The copy machines and the desk phones and the computer monitors have all gone quiet, waiting for morning in the way that buildings always wait, patiently, steadily, without any particular urgency. And yet, if you were to slip inside that building tonight and walk slowly through its lowest levels, down past the loading dock and into the mechanical rooms beneath the lobby, you would find something still awake. Not loudly awake, not brightly awake, but present, alert in a very quiet, very steady way. There are panels with small indicator lights glowing softly in shades of green and amber. There are circuits that are still carrying current, still watching, still measuring. There are systems designed to do one thing above all others: to make sure that if something changes in the world outside, this building will be ready. These are the emergency power systems. And in the nighttime hours, when the building is at its most still, they feel perhaps most like themselves, most at home in the quiet, most at ease in their work. We spend a great deal of time thinking about the parts of a building we can see, the glass facades and the painted corridors, the conference rooms and the coffee stations, the things that serve us when we are present and awake. But a building has another layer entirely. It has systems that are not meant to be noticed, systems that run continuously and quietly, tucked into rooms most people will never visit, doing work that most people will never think about. Emergency power systems belong to that hidden layer. They are part of the building's deeper infrastructure, the part that exists not for convenience, but for continuity. The goal of an emergency power system is a simple one, if you say it plainly. When the normal source of electricity becomes unavailable, something must step in and keep the most critical functions of the building running. The lighting in the stairwells, the pumps that supply water to sprinkler systems, the equipment in operating rooms, the controls for smoke exhaust fans, the things that, in a moment of disruption, matter most. But what makes a good emergency power system remarkable is not just what it does during a crisis. It is how it behaves in all the hours before one ever arrives. Because the most important thing about emergency power, the thing that defines a truly well-designed system, is that it must always be ready. Not ready in a dramatic sense, not ready in a way that calls attention to itself or demands acknowledgement, ready in the way that a good foundation is ready, steadily, silently, without interruption. Quiet readiness is, in a real sense, the goal. The emergency power system should be present without being intrusive. It should watch without drawing any notice, and when the moment comes that it is truly needed, it should respond so smoothly, so reliably, that the people depending on it may not even fully realize it was ever absent. The most successful emergency power system, in many ways, is the one that most people never think about at all. Let's stay with that image for a moment. A building late at night. Perhaps it is a mid-rise office building, 12 stories of glass and steel, sitting quietly on a corner in the downtown of a mid-sized city. The parking garage is nearly empty. The lobby has a single dim light on above the security desk, where a guard is sitting with a cup of coffee, watching a small monitor. Somewhere outside, power lines trace their way through the city on tall steel towers and wooden poles. They carry electricity generated far away, from a plant on the edge of the city or a substation many miles distant, and they bring it here to this building through a service entrance on the north side of the ground floor. The power arrives step by step through transformers and switchgear and metering equipment until it reaches the building's main electrical room. That electrical room is a quiet place at this hour. A row of large electrical panels lines one wall. A main switchboard stands near the center of the room, its painted steel cabinet warm to the touch from the steady flow of current inside. The lights in the room are dim. The air smells faintly of warm insulation and metal. Everything in this room is functioning normally. The current is flowing. The building is receiving its power just as it should be. And somewhere nearby, in a cabinet that may not even carry any obvious label from the outside, a monitoring system is watching. It is watching the incoming utility power with great care and great patience and no particular drama. Utility power monitoring is, in its essence, the practice of observing the characteristics of the electricity arriving from the power company, and continuously checking whether those characteristics fall within acceptable limits. It is quiet work, continuous work, the kind of work that happens in the background every second of every hour, and that produces no visible activity at all when everything is as it should be. What specifically is being watched? Voltage is one of the primary things. Voltage is the measure of electrical pressure, the force, in a sense, that pushes current through the building circuits. Normal commercial utility voltage arrives at a specific level, and it is expected to stay reasonably close to that level. If the voltage drops significantly below where it should be, the building's equipment may not function properly. Motors can labor, sensitive electronics can behave unpredictably, critical systems may begin to falter. A well-designed monitoring system notices a voltage drop early. It does not wait for the problem to become obvious. It watches the levels continuously, and when they drift outside the acceptable range, it takes note. Something has changed. Something may need to happen. Frequency is another characteristic being observed. In North America, utility power is delivered as alternating current at 60 cycles per second, 60 Hertz. That frequency is remarkably stable under normal conditions, maintained carefully by the utility company. But when a power grid is under stress, when generation and load fall out of balance, frequency can shift, and a monitoring system that is paying close attention will see that shift long before most equipment begins to complain. Then there is phase. Many commercial buildings receive power not as a single-phase supply, but as a three-phase supply, 3 separate electrical conductors, each carrying current at a different point in the same alternating cycle. Three-phase power is more efficient for large equipment, and it is standard in commercial and industrial buildings of any meaningful size. The monitoring system watches all 3 phases. If one of them goes missing, if a phase loss occurs, the monitoring system will detect it because the careful balance that should be present among the 3 conductors will have been disturbed. Together, these 3 things, voltage, frequency, and phase, paint a continuous picture of the health of the incoming utility supply, and the monitoring system watches them all quietly in the background, in a room that most people in the building above will never visit. There is something gentle in this kind of vigilance. It is not anxious. It does not watch for problems the way something tense might watch, bracing itself for bad news. It simply observes. It holds its threshold values with calm certainty. This is normal. This falls within acceptable limits. And it notes with equal calm when those limits are exceeded. The monitoring system also helps make a distinction that matters quite a lot in emergency power design. There is a difference between a brief flicker and a true outage, between a momentary sag in voltage and a genuine loss of the utility supply, and the monitoring system is designed to help separate one from the other. Power systems flicker. It is simply part of how they behave. A heavy motor starting somewhere on the same circuit can pull the voltage down for a fraction of a second. A distant fault that is quickly cleared can cause a brief interruption. These events happen regularly, and the vast majority of them resolve themselves in far less time than it would take any person to react. If an emergency power system responded to every flicker, if it treated every brief sag in voltage as a true emergency, it would be activating and resetting constantly. The equipment would wear prematurely. The power transitions would be more disruptive than the brief disturbances they were trying to address. And so there is, built into the monitoring logic, a kind of patience. A brief window of time, sometimes just a second or two, sometimes a few seconds more, depending on the application, during which the system observes the disturbance and waits. Is this still happening? Is this getting worse? Or has the utility already recovered on its own? For most disturbances, the answer is that the utility recovers, the flicker passes, the voltage returns. The monitoring system settles back into its quiet watching, and nothing further happens. But for a true outage, for a genuine loss of power that persists, that deepens, that shows no sign of reversing, the monitoring system recognizes what it is seeing, and it begins to prepare. The preparation is quiet at first. There is no alarm, no light suddenly flooding the room. The building above continues its nighttime stillness, entirely unaware. What happens instead is a change of state. A relay closes, a signal is sent. Somewhere else in the building, other equipment receives that signal and begins its own preparation in return. The monitoring system has done its part. It has watched, it has distinguished, it has reached a conclusion calmly and automatically, with no human involvement required. The loss of utility power has been detected. It has been confirmed as real, and now the next stage of the response can begin. This is one of the quiet virtues of a well-designed system. The response does not depend on someone being present to notice. It does not require a facilities manager to look up from a desk, or a guard to call a maintenance line, or anyone at all to make a decision. The building watches itself, and when the conditions require a response, the response begins. In hospitals, this automatic quality is not merely convenient, it is essential. Somewhere down a corridor, in an operating room, there may be a procedure underway. There may be a patient on a ventilator. There may be monitoring equipment displaying values that must not be interrupted. The people in that room cannot pause their work to wait for someone to notice that the utility supply has failed. The system must know. The system must act. And it does, because that is what it was designed to do. In the electrical room, the monitoring equipment continues its work. The panels are still dim. The indicator lights still glow softly, though perhaps a small amber indicator that was dark a moment ago has now come to life somewhere on a status panel, noting quietly that the utility supply has been found wanting. The building above remains still. The guard at the security desk may not have noticed anything yet. The coffee in the cup is still warm. The monitor on the desk still glows softly, but something is already in motion, quietly, automatically, in the background, as it was always meant to be. In the rooms deeper in the building, other systems are stirring. A generator resting in standby is receiving a signal. Transfer switches are preparing to make a decision. The machinery of continuity, the invisible infrastructure that keeps a building protected even in the dark, is beginning to wake. We will follow that process step by step in the moments ahead. But for now, simply rest with the image of the monitoring system at work. The quiet room, the softly glowing panels, the steady measurement of voltage and frequency and phase, the patient observation that never stops, that never sleeps, that continues through every dark hour, watching the building's power supply the way a lighthouse keeper once watched the sea, calmly, without drama, ready for anything. The building is still, the systems are awake, and somewhere in the hum of the electrical infrastructure, everything is quietly, steadily prepared. The signal has been sent. It traveled quietly through wiring that runs inside conduit, through conduit that runs inside walls, through walls that most people in this building have never thought about. It carried no sound. It produced no light that anyone upstairs would notice. It was simply a change of state, a contact closed, a circuit completed, a small electrical message moving from one piece of equipment to another in the darkness of the mechanical level. And now somewhere in this building, a piece of equipment that has been waiting, patiently without complaint, for days or weeks or possibly longer, has received that message and is preparing to act. This is where we follow the signal, deeper into the building, further from the lobby and the hallways and the ordinary spaces of the day, down into the rooms that exist not for people, but for systems, the rooms that are always lit by the same dim fluorescent glow, always faintly warm, always carrying the low hum of equipment doing its quiet, necessary work. Let us think for a moment about what it means to transfer power. When utility electricity flows into a commercial building, it arrives from one direction and one source. It comes in through the service entrance, passes through metering equipment, and then distributes itself through the building's electrical system like water spreading through pipes. Every panel, every circuit, every outlet and fixture and motor draws from that single upstream source. It is, under normal conditions, entirely sufficient. The utility company maintains it. The voltage is steady, the frequency is consistent, and no one in the building needs to think about it at all. But an emergency power system introduces a second source, a backup, an alternative that stands ready to supply the building's most critical loads if the first source ever fails. And the moment that first source fails, or rather, the moment the monitoring system decides it has failed, a decision must be made. Which source should be feeding these loads right now? That decision and the physical act of carrying it out belongs to the automatic transfer switch. The automatic transfer switch is, in its essential nature, a selecting device. It does not generate power. It does not store power. It simply chooses, at any given moment, which of two available sources will be connected to the loads downstream of it. And it carries out that choice automatically, without waiting for any person to turn a dial or push a button or make a phone call. In its enclosure, a metal cabinet, usually painted gray or beige, mounted to the wall of an electrical room or a dedicated transfer switch room, the automatic transfer switch contains mechanisms that are perhaps more elegant than their humble industrial appearance might suggest. There are heavy-duty contacts built to carry substantial current. There are control components that watch for signals and respond to them. There is logic built into the device that knows the sequence: watch, decide, transfer, confirm. The word automatic in the name is perhaps the most important word, because the great virtue of the automatic transfer switch, the reason it exists, the reason it is required in so many building types by code, is precisely that it removes human delay from the equation. Human delay, in the context of a power failure, is not a small thing. A person must notice that the power has gone out. They must locate the right equipment. They must understand what needs to be done. They must do it. And all of this, even in the most efficient and well-trained scenario, takes time. Time that a hospital patient on a ventilator does not have. Time that a smoke exhaust system controlling the spread of fire in a stairwell cannot afford to wait. The automatic transfer switch removes all of that time from the equation. The response begins not when someone notices, but when the monitoring system detects, which is to say, it begins almost immediately. The sequence itself unfolds in a particular way, and there is something almost meditative in following it step by step. The monitoring system, which we followed so carefully in the previous chapter, watching voltage and frequency and phase with its patient, continuous attention, has determined that the utility source is no longer acceptable. The signal has been sent, and now the automatic transfer switch is involved. First, the transfer switch receives the signal and confirms what it is being told. The normal source has been lost or has degraded below the threshold at which it can reliably serve the building's loads. This confirmation is not instantaneous. There is a brief, intentional delay built into the logic, a moment of measured waiting that serves a purpose. It ensures that a very brief disturbance does not trigger a full transfer unnecessarily. But if the disturbance persists, if the signal continues, if the normal source remains unsuitable, the transfer switch proceeds. It initiates the start signal for the emergency generator, and then it waits. This waiting is one of the quieter and more precise moments in the entire sequence. The transfer switch knows that the generator needs time to start, time to come up to speed, time for its voltage and frequency to stabilize at the values required before it can safely serve the building's loads. The transfer switch will not rush this. It will not connect the emergency source until that source is ready. And so there is a window of time, typically measured in seconds, sometimes 10 seconds, sometimes a few more, during which the building's emergency loads are without power. The corridors fed by the emergency system are dark. The critical panels are waiting. The transfer switch is holding, patiently and precisely, for the generator to become ready. This is the gap that UPS systems and battery-backed devices exist to bridge, but we will come to those in their own time. For now, we stay with the transfer switch, waiting in its cabinet, watching for the signal that the generator is ready. When that signal comes, when the emergency source has stabilized and proven itself acceptable, the transfer switch acts. Its contacts move. The connection to the failed utility source is opened. The connection to the emergency generator is closed. and power begins to flow again from a new direction to the loads that need it. The transfer is complete. In a well-designed building with a well-maintained system, the people upstairs may experience this entire sequence as a brief dimming of lights, or perhaps nothing at all, a moment of quiet, a pause so small it might be dismissed as imagination, and then continuity, the lights steady, the equipment running, the building composed. This is the ambition of the transfer switch, not to be dramatic, not to announce itself, but to carry out its function so cleanly, so reliably, that the disruption it is managing becomes almost imperceptible to the people it is protecting. The transfer switch is, in the truest sense, a system that succeeds by going unnoticed. Some buildings have one transfer switch. Some have many, a separate switch for each category of emergency load, arranged so that life safety circuits, critical care circuits, and equipment circuits can each be managed independently. In larger facilities, a room may be devoted to transfer switches entirely. A quiet space filled with gray cabinets, each one watching its portion of the building, each one ready to make its selection when called upon. Those rooms have a particular quality to them at night. The equipment is still, the cabinets are warm. Small indicator lights, green for normal source, perhaps amber for transfer position, glow steadily in the dimness. There may be a faint mechanical sound, the kind of sound that is not quite a hum and not quite a click, the sound of readiness in physical form. And everything in the room communicates the same message. We are watching. We are ready. Nothing will be required of anyone here tonight, but if it were, we would act. Now, let us follow the start signal as it travels. Because while the transfer switch was receiving its instructions and preparing to act, another process was already beginning somewhere else in the building, or perhaps behind the building or beside it, in a structure purpose-built to house the machine that emergency power ultimately depends upon. The generator room, if there is one space in the entire emergency power infrastructure that earns the word room in the fullest sense, a space with presence, with weight, with a particular atmosphere that is unlike any other part of the building, it is the generator room. It is usually a large space with poured concrete floors and heavy walls built to contain both the mechanical force and the sound of the equipment inside. The ceiling may be high. Ventilation louvers line the exterior walls because the machine inside will need air, large quantities of it, when it runs. There may be the smell of diesel fuel, faint but unmistakable, a smell that speaks of stored energy and mechanical potential. And at the center of the room, or along one of its walls, stands the generator itself. It is a substantial piece of equipment. A diesel engine, sometimes the size of a large truck engine, sometimes considerably larger, is coupled directly to an alternator, the component that converts the engine's mechanical rotation into electrical power. Together, they form the generator set. The engine and the alternator, bolted to a common base frame, connected to fuel lines and exhaust piping and cooling systems and electrical control panels, all of it assembled into a machine that has one purpose and serves it with complete dedication. In standby mode, the generator is still, the engine is not running, the alternator is not turning. The room is quiet except for perhaps the faint sound of a block heater, an electric element that keeps the engine coolant warm, ensuring that when the start signal arrives, the engine will turn over smoothly and quickly, rather than laboring against the resistance of cold metal. The block heater is a small detail, but it matters. It is one of the many ways that a well-maintained emergency generator is never truly off. It is always being cared for, always being prepared. The coolant is warm. The battery that powers the starter motor is being kept charged by a small trickle charger connected to utility power. The fuel in the tank has been tested and treated so it will flow cleanly when needed. The oil has been changed on schedule. The air filters are clean. All of this preparation happens in advance, in the ordinary hours, so that when the extraordinary moment arrives, the machine is ready. When the start signal reaches the generator's control panel, that small but important cabinet mounted on the side of the generator set, its own indicator lights glowing softly in the dim room. The sequence begins. The control panel sends current to the starter motor. The starter motor engages the engine's flywheel. The engine turns, and within a few seconds, sometimes fewer, the diesel combustion cycle catches. The engine fires and the generator set comes to life. The sound of this in the generator room is unmistakable. It begins as a low mechanical churning, the sound of an engine finding its rhythm. It builds quickly, deepening and steadying as the engine reaches operating speed. Within moments, the exhaust note settles into something consistent and even, a low, powerful thrum that travels through the floor of the generator room and into the structure of the building itself, a vibration that the walls can feel even if the people 2 floors above cannot quite hear it. The alternator, turning now at the speed required to produce 60 cycle current, begins to generate voltage. The control system watches. It monitors the output. It waits for the voltage and frequency to stabilize within acceptable limits, the same kind of limits that the utility monitoring system watches on the incoming power side. And when those limits are met, when the generator's output has proven itself steady and suitable, the control panel sends its confirmation back to the transfer switch. The generator is ready. In the transfer switch room, or wherever the transfer switch cabinet stands in its quiet vigil, the confirmation is received. The contacts move. The building's emergency loads are connected to the generator's output, and power flows smoothly, steadily from the spinning alternator in the generator room through cables and panels and circuits to the lights and equipment that have been waiting in the brief darkness. The corridor lights come back on. The exit signs, which were battery-backed and never went out, are now being supplied by the generator instead of their internal cells. The critical panels are energized. The equipment downstream begins to resume its operation. The building is, in the most important sense, restored, and yet the generator room remains in its state of steady, purposeful activity. The engine continues to run, the alternator continues to turn, the fuel continues to flow from the storage tank through the supply lines to the injection system. The cooling system manages the engine's temperature. The exhaust travels through insulated piping to the exterior of the building, where it exits quietly into the night air. The generator will continue running for as long as it is needed. It does not grow impatient. It does not tire in the short term. It was built to sustain exactly this kind of operation, to run for hours or longer if the situation requires it, reliably and without drama, while the building above continues its functions as normally as possible. In this way, the emergency generator is perhaps the most active expression of a principle that runs through every part of emergency power design. The principle of quiet readiness transformed into quiet action, a system that spent its standby hours doing nothing visible, simply being maintained, being exercised on a schedule, being kept warm and charged and fueled, and that now, in the hour it was designed for, is doing exactly what it was always meant to do, without announcement, without ceremony, simply running steadily in the warm and faintly humming dark of the generator room, while the building it serves continues on. And so the building breathes again. Not as it did before, the utility supply is still absent, and that absence has not yet been resolved, but in a sustained and reliable way that keeps the most important things intact. The stairwells are lit. The critical systems are powered. The people who depend on this building, in whatever way they depend on it, are protected. The generator runs on. The transfer switch holds its position. The monitoring system continues to watch, now watching both the failed utility source and the active emergency source, noting the status of each, waiting for the moment when the utility supply recovers and the retransfer sequence can begin. But that moment has not yet come, for now the night continues. The generator room hums with its low, steady sound. The transfer switch room is still and warm. The indicator lights glow their patient greens and ambers in the dimness. The building is held. Everything that matters is still running. And somewhere in the quiet machinery of all these hidden rooms, the emergency power system is doing what it always promised it would do: keeping watch, keeping current, keeping the darkness at bay. Rest now with that image. The generator running steadily in its room, the transfer switch holding its careful position. The building above, composed and continuous, unaware of the labor being done on its behalf in the rooms below. The systems are awake, the building is safe, and the night moves gently on. We spoke in the last chapter of a gap. It was a brief gap, measured in seconds, not minutes. The space of time between the moment the utility supply failed and the moment the generator finished waking and the transfer switch completed its handoff. A window so narrow that many people in many buildings would experience it, if they experienced it at all, as nothing more than a momentary dimming, a soft interruption, a held breath. But in some buildings and for some equipment, even that narrow window is too wide. There are loads in the world of emergency power, particular pieces of equipment, particular systems, particular functions that cannot tolerate any interruption at all. Not a second, not half a second, not even the briefest loss of continuous power flow without consequences that range from inconvenient to genuinely dangerous. A server processing a transaction, a medical monitor displaying a patient's heart rhythm, a control system managing a critical industrial process. For these loads, the gap that the generator's startup time creates is not a small problem. It is the central problem, and it is the problem that the uninterruptible power supply exists to solve. The uninterruptible power supply, the UPS, is in its most fundamental character a bridge, a span of stored energy thrown across the gap between utility failure and generator readiness, narrow enough to cross quickly but strong enough to hold whatever passes over it. It does not replace the generator. It is not designed to power a building through a long outage the way a generator can. It serves a different and more specific role: to ensure that in the seconds, and sometimes the minutes, when neither the utility nor the generator is available to serve a particular load, something is. Continuously, without interruption, without so much as a flicker. The UPS accomplishes this through a combination of components working together, and it is worth spending a quiet moment with each of them, because together they form a picture of a system that is, at its core, about the patient accumulation and careful release of stored energy. At the heart of any UPS is a bank of batteries. These are not the small batteries of consumer devices, not the kind that fit in a drawer or power a remote control. They are purpose-built cells, often lead-acid or lithium-based depending on the application, arranged in strings and cabinets and enclosures designed specifically for the job of storing electrical energy in quantity. In a large commercial or hospital UPS installation, the battery cabinets may fill an entire section of an electrical room or occupy a dedicated space of their own. They are heavy, they are carefully ventilated, and they are, at every moment during normal operation, in the process of being kept fully charged and ready. This charging is handled by the UPS's rectifier, a component that takes the incoming alternating current from the utility supply and converts it into the direct current that the batteries require. The rectifier works quietly and continuously, keeping the batteries at their proper state of charge, ensuring that when the moment of need arrives, the stored energy is there in full. And on the other side of the batteries, waiting to convert that stored direct current back into the alternating current that the downstream equipment requires, is the inverter. The inverter is the component that, in the event of a power failure, takes over the task of supplying the load. It draws from the batteries and produces, from that stored energy, a steady and controlled output, voltage and frequency held precisely within the limits that sensitive equipment demands. In most modern UPS designs, the inverter is not simply a backup that activates when needed. It is continuously active, continuously supplying the load, with the batteries and the utility both present behind it, in a configuration that means the load never draws directly from the raw utility source at all. The load draws from the inverter draws from the batteries. The batteries are kept charged by the rectifier, and the rectifier draws from the utility. This arrangement, sometimes called double conversion, means that from the perspective of the equipment downstream, there is no utility. There is only the inverter, a clean, regulated, continuous source of power that does not flicker when a truck starts outside, does not sag when a large motor comes online elsewhere in the building, and does not disappear when the utility fails. It simply continues. When the utility does fail, the rectifier stops receiving its input, the battery charging stops, and the batteries begin to discharge. But the inverter keeps running. The output to the load keeps running. From the perspective of the servers or monitors or control systems downstream, nothing has changed at all. This is the UPS at its most elegant, invisible in the transition, seamless in the handoff, achieving through careful design exactly the outcome that the equipment it serves requires, continuity so complete that the failure it is bridging is never felt at all. The batteries, of course, will not last forever. This is the designed reality of the UPS, and it is not a flaw. It is simply the nature of stored energy. A battery can hold only so much, and so the UPS is not designed to carry its load indefinitely. It is designed to carry it long enough for the generator to start, long enough for the transfer switch to complete its handoff, long enough for the critical equipment downstream to receive generator power before the batteries are depleted. In most commercial applications, UPS systems are sized to provide somewhere between 5 and 30 minutes of runtime, depending on the load and the design intent. Some hospital and data center applications call for longer run times. Some smaller installations need only a few minutes. The sizing is deliberate, chosen to match the expected generator start time with a margin for safety and for the unexpected. When the generator comes online and the transfer switch delivers generator power back to the UPS's input, the rectifier begins charging the batteries again. The gap has been crossed, the load has been held through the transition, and the UPS settles back into its normal operating state. Inverter running, batteries charging, the downstream equipment entirely unaware of what just happened. A UPS that has done its job well leaves no evidence that it has done anything at all. The equipment it protects simply kept running. The data was not lost. The monitoring trace did not miss a beat. The process did not interrupt. And in the quiet of the electrical room or the battery room, or wherever the UPS cabinet stands with its own small panel of indicator lights, those lights continue their patient glow. Green for normal, no alarms, no flags. Everything as it should be. Battery health is one of the quiet obligations of a well-maintained UPS installation. The batteries are the soul of the system, the stored energy that makes everything else possible, and they must be cared for with consistency. Batteries age. Their capacity diminishes gradually over time. A battery string that was sized to provide 15 minutes of runtime when it was new may provide only 10 minutes after several years of service. And if that diminished capacity is not detected and addressed, the gap the UPS was designed to bridge may grow wider than the batteries can now span. And so the health of the batteries is checked, not constantly, not dramatically, but on a schedule, measured, recorded, compared against baseline values, impedance tests, load bank tests, runtime verifications, all of it quiet work, carried out in the background, producing numbers that sit in maintenance logs and inform replacement schedules and ensure that the stored energy the system depends upon is genuinely there when it is needed. This is one of the less visible rhythms of emergency power maintenance. The UPS does not announce that its batteries are aging. It does not slow down or flicker or otherwise signal the passage of time. It simply runs, as it always has, while the gradual work of capacity loss proceeds silently inside the battery cabinets. Only the testing reveals what is actually there. Only the maintenance preserves it. And so someone, somewhere on a regular schedule goes to the battery room or the electrical room and performs the quiet work of verification. They check the values, they compare them to the expectations, they make notes, and the system continues, maintained and honest and ready. Let us leave the UPS now. Leave it running in its cabinet, inverter steady, batteries quietly holding their charge, and move into the building, up from the mechanical levels, up through the utility spaces and the service corridors, into the floors where people work during the day, and where, at this hour, no one is present. Into the spaces that are dark now, or nearly dark, except for one particular kind of light that belongs entirely to the nighttime, entirely to the emergency context, and that gives a building a quality at night that it does not have during the day. The emergency lights are on, not everywhere, not in the way that normal lighting fills a space with even comfortable illumination designed for work and reading and the ordinary tasks of the day. Emergency lighting works differently. It is purposeful and specific, placed where people will need it most in a moment of disruption, and its light, while modest, has a quality of its own. It is steady, unwavering, unhurried. Walk down a corridor in a darkened commercial building when the normal lights are off but the emergency lighting is active, and you will notice immediately that the space looks different. The ceiling fixtures are dark. The workstations and conference rooms on either side are in shadow, but at intervals along the corridor, at the intersections near the stairwell doors, above the exit signs, there is light, low and even and clear enough to see by, enough to walk by, enough to know where the stairs are and which way leads out and what lies ahead. This is the design intent of emergency lighting, stated as simply as it can be. When the normal lighting fails, emergency lighting ensures that a person in the building is not left in complete darkness. It ensures that the paths to exits remain visible, that the stairwells can be navigated, that the way out of the building is readable even under the most difficult circumstances. Emergency lighting is, at its core, a life safety system, not a comfort feature, not an aesthetic choice. It is part of the same essential infrastructure as the fire alarm and the sprinkler system, one of the things a building provides not for productivity or convenience, but for the protection of the people inside it. The exit sign deserves a particular moment of attention because it is perhaps the most continuously present piece of emergency power infrastructure in any building. Unlike the generator, which rests in standby, unlike the transfer switch which waits in its cabinet, unlike the UPS which works quietly behind the scenes of a specific set of loads, the exit sign is simply always on. Right now, in every corridor and stairwell of the building we have been imagining tonight, exit signs are glowing. Their letters, red or sometimes green depending on the jurisdiction and the era of installation, are illuminated with a calm and steady light that does not respond to the hour, does not dim when the building empties, does not notice the difference between a busy Tuesday afternoon and a quiet Thursday night. It is simply always there, always pointing the way, always ready to guide whoever might need guiding. The exit sign is powered in one of several ways depending on its type and its location in the building's electrical system. Some are connected to the emergency branch of the building's power system and receive their energy from whatever source, utility, or generator is currently supplying that branch. Others have their own internal battery, a self-contained power source that keeps the sign illuminated even if the circuit feeding it is lost entirely. Many modern installations use both, a connection to the emergency circuit for normal operation, with an internal battery as a final backup layer. This layering is characteristic of how life safety systems in general are designed. Not one protection, but several. Not a single path of reliability, but multiple overlapping paths, so that the failure of any one component does not leave the building unprotected. The emergency lighting fixtures themselves, the dedicated units mounted at low points on walls or recessed into ceilings at specific intervals or positioned at the tops and bottoms of stairwells, operate on similar principles. During normal power conditions, they are connected to the building's electrical system, and their internal batteries are being kept fully charged, just as the UPS batteries are kept charged. The fixtures are illuminated normally in many cases, indistinguishable from regular lighting when everything is working as it should. When normal power is lost, the fixtures detect the loss. A small sensing circuit inside each unit monitors the incoming supply, and they switch immediately and automatically to battery power. The transition is essentially instantaneous. The light does not go out and come back on. It simply continues, now drawing from stored energy rather than from the building's circuits. The battery in a self-contained emergency lighting unit is sized to sustain illumination for a minimum period. In most commercial applications in North America, the requirement is 90 minutes of emergency operation. 90 minutes is the envelope within which evacuation is expected to occur, within which emergency responders are expected to arrive, within which the building's occupants should be able to reach safety. 90 minutes of light. Calm, steady, patient light. Enough to see by. Enough to navigate by. Enough to keep the darkness from becoming disorienting or frightening. Testing emergency lighting is one of the quiet rituals of building maintenance. Because the failure mode of an emergency light is a particular kind of invisible failure, the fixture looks entirely normal during ordinary operation, lit and functioning like any other fixture, until the moment its battery is called upon and found to be insufficient. The only way to know whether the emergency battery will hold is to test it, to simulate the loss of normal power and observe whether the fixture continues to illuminate for the required duration. In some buildings, this testing is done manually on a schedule by maintenance staff who move through the corridors with clipboards and flashlights, pressing the test buttons on individual fixtures and noting whether they illuminate, whether they hold their output, whether their batteries are healthy. In more sophisticated installations, the testing may be automated, centrally controlled systems that initiate tests on a programmed schedule and report results back to a monitoring panel, flagging any fixture that has failed or degraded without requiring anyone to walk the corridors to find out. Either way, the testing happens, quietly, on a schedule, in the background of ordinary building operations, and the result is the same: confidence that when the corridor is dark and the normal lights are out and someone is moving through the building trying to find their way to safety, the emergency lights will be there, glowing at the right intervals, pointing toward the exits, holding their charge for the full 90 minutes or more that the design intended. Step into the stairwell now. It is a simple concrete stairwell, the kind found in nearly every commercial building, painted gray or white with metal handrails and non-slip nosing on each step. During the day, when the building is occupied and the normal lighting is active, this stairwell is adequately, if not generously, lit. It is functional. People move through it quickly without particular thought. At night, with the normal building lighting dark, the stairwell is a different kind of space. The emergency lighting units positioned at each landing cast pools of steady illumination that reach the steps but leave the high corners of each stairwell in shadow. The exit signs above each doorway glow red or green, marking the exits to each floor. The space is entirely navigable, entirely safe. But it has a quality of stillness, of purposeful quiet, that it does not carry during the day. This is the stairwell as the emergency power system intended it. Not bright, not crowded with light, simply clear, simply sufficient. A path that can be followed without confusion, without fear, by anyone who needs it. The emergency lighting in that stairwell will continue to hold for as long as its batteries or its generator-fed circuit can sustain it. It is not waiting for anything. It is not building toward anything. It is simply doing what it was placed there to do, illuminating the path, holding the darkness at bay, remaining present in the way that all the best emergency systems remain present. Calmly, steadily, without needing to be noticed, without requiring anything from anyone. The building is dark except where it needs to be lit. The generator runs in its room below. The UPS holds its loads through the quiet inverter. The transfer switch maintains its position. And in every corridor and stairwell, the emergency lights glow on. The night continues, the systems continue, and everything that needs protecting is protected. Rest with that. The soft light in the corridor, the steady glow of the exit signs, the warmth of the UPS cabinet, and the low hum of the generator room filtering up through the floors. A building that is held carefully and completely by systems designed for exactly this moment. The darkness has not won here. It was never going to. There is a quality that the best emergency power components share, and it is one that takes a moment to fully appreciate. It is not speed, though many of them act quickly. It is not size, though some of them are very large. It is not complexity, though they are carefully engineered. The quality is this: they are most themselves when they are doing nothing visible at all. The generator in its room, resting with warm coolant and a charged starter battery, waiting for a signal that may not come for months. The transfer switch in its cabinet, holding the normal source connection with calm mechanical certainty, neither rushing nor hesitating, the UPS inverter running its quiet, continuous loop, the batteries behind it fully charged, the downstream equipment entirely unaware of the protection surrounding it. All of these systems spend the great majority of their working lives in a state that looks, from the outside, like inactivity. They are present, they are maintained, they are ready, but they are not visibly doing anything. And nowhere is this quality more purely expressed than in the battery. The battery is perhaps the most philosophically interesting component in the entire emergency power infrastructure, for a simple reason. Every other major component in the system involves active machinery. Generators have engines and alternators. Transfer switches have moving contacts. UPS systems have rectifiers and inverters and control electronics. Even the monitoring equipment has circuits that are continuously processing and comparing and deciding, but the battery just holds. It does not move, it does not process, it does not decide. It is a vessel of stored potential, energy that was placed inside it during the charging process, and that sits there, available, patient, present, waiting for the moment it is called upon to give itself back. In a building's emergency power infrastructure, batteries appear in many forms and in many places. We have already spent time with the large battery strings inside the UPS cabinet and with the smaller cells inside individual emergency lighting fixtures. But batteries appear elsewhere too, in roles that are equally quiet and equally essential. The generator's control system depends on a battery, typically a lead-acid unit, not unlike a heavy-duty automotive battery, to power the starter motor that turns the engine over during those first critical seconds of startup. Without that battery, the start signal from the transfer switch would arrive and find no energy to act on. The engine would not turn, the generator would not start. The entire carefully designed sequence that follows utility failure would stop at its first step. This battery, like all the batteries in the system, is kept on a continuous trickle charge during the long periods of standby. A small charger connected to utility power delivers a gentle and steady current that keeps the battery at full capacity without overcharging it. The charger works so quietly and draws so little attention that it is easy to forget it is there. But it is there. Every hour of every day, during all the standby time between exercises and between actual emergencies, the charger is doing its work, keeping the battery ready, ensuring that when the start signal finally arrives, the energy to respond to it is fully present. Battery systems in commercial emergency power applications require a particular kind of ongoing attention, and it is worth sitting with what that attention looks like in practice. A battery does not announce its own decline. This is one of the fundamental truths of battery-dependent systems, and it is the reason that maintenance practices around batteries are so deliberate and so specific. A battery that is aging, losing capacity, increasing in internal resistance, approaching the point where it can no longer deliver its rated energy, may look entirely normal from the outside. The cabinet is the same. The indicator lights on the charger show normal. The voltage under light load appears acceptable. But put that battery under the full demands of an actual discharge, a real emergency, a genuine transfer to backup power, a sustained run at the current levels the system actually requires, and the insufficiency that was invisible during normal operations becomes immediately and consequentially apparent. This is why testing matters so deeply in battery maintenance, not periodic glances, not casual visual inspections, but actual testing, load testing, impedance testing, capacity verification, that exercises the battery under conditions that reveal its true state rather than its apparent one. Load bank testing, in particular, is one of the more honest conversations a building can have with its battery systems. A load bank is a device that draws a controlled and known amount of current from the battery, simulating the actual demand the battery would face during a real emergency. The battery is discharged under this controlled load while its voltage is monitored carefully. How does the voltage hold as the discharge proceeds? How quickly does it drop? How long does the battery sustain acceptable output before it falls below the minimum threshold? The answers to these questions tell the truth about battery capacity in a way that nothing else quite can. And so the maintenance log fills, page by quiet page, with test records and capacity measurements and replacement dates and charger inspections, all of it accumulating into a picture of battery health that is current and honest and actionable. All of it ensuring that when the building actually needs its stored energy, that energy is genuinely there. One of the most important but least glamorous aspects of battery maintenance is also one of the most atmospheric in a quiet way. Battery rooms, the dedicated spaces in larger installations where battery strings are housed in their racks and cabinets, have a particular character. They are clean rooms, or should be. Batteries, especially lead-acid batteries under charge, can release small amounts of hydrogen gas, and so battery rooms are ventilated carefully, either naturally or mechanically, to prevent any accumulation. The air in a battery room has a faint particular quality, not unpleasant but specific, slightly cool, slightly metallic. The batteries themselves, in a large UPS or generator support installation, are arranged in long rows on steel racks. Each cell or module is connected to the next with heavy copper interconnects, building up the strings of voltage and capacity that the system requires. The whole assembly is dense and orderly and, in its way, quite beautiful, the product of careful engineering translated into physical form. In the quiet of the night, a battery room is one of the most still spaces in the entire building. Nothing moves, nothing rotates, nothing flows in any mechanical sense. The energy stored in those racks of cells is entirely latent, present but invisible, potential but not yet kinetic, waiting, as batteries always wait, for the moment they are needed. The only sound, if there is one, might be the faint hum of the ventilation system doing its quiet work, or the barely perceptible sound of the charger working at its trickle rate, or nothing at all. Just the building settling around the battery room and the batteries sitting in their racks, holding everything they have been given. Now, let us follow the energy outward. When the batteries discharge into the UPS inverter, or when the generator begins supplying its output, or when the transfer switch completes its handoff and emergency power begins to flow, where does it go? Through what pathways does it travel? How does it move from its source deep in the mechanical and electrical rooms of the building to the specific loads it is meant to serve? This is the domain of emergency distribution. The wiring, the panels, the conduit, the protective devices, and the carefully planned architecture of circuits that carry emergency power from its sources to its destinations. It is, like everything else in this system, designed to be invisible, tucked behind walls, routed through ceilings, hidden in conduit that most people in the building will never see and would not be able to identify if they did. But the architecture of emergency distribution is not arbitrary. It follows a logic, a deliberate logic, shaped by code requirements and engineering judgment and the hard-won experience of what happens when power systems are not carefully organized. That is worth understanding. The central principle of emergency distribution is separation. Emergency circuits must be kept separate from normal power circuits, not loosely separate, not separated wherever convenient, genuinely, physically, consistently separate, in their own conduit, on their own wiring pathways, protected by their own devices, served by their own panels. Separate enough that a failure in the normal power system cannot reach across and affect the emergency system. Separate enough that a fault in a normal circuit cannot take down an emergency circuit at the same time. The reason for this separation is straightforward when you consider the alternative. Imagine an emergency power system that shares conduit with normal circuits. A fault develops somewhere in the normal wiring. A short circuit, a ground fault, an insulation failure. The fault is cleared by a protective device, which is exactly what should happen. But if the emergency circuit sharing that conduit was also affected, if the same fault that took down the normal circuit also took down the emergency circuit, then the building has lost both its primary and its backup power to that area simultaneously. The emergency system has failed not because it was poorly designed in itself, but because it was not adequately separated from the system it was meant to back up. Separation prevents this. It ensures that a common mode failure, a single event that could theoretically affect both systems at once, is not possible, or at least not possible along the wiring pathways. The emergency system stands apart, insulated from the vulnerabilities of the normal system, able to survive whatever caused the normal system to fail. In practice, walking through the electrical infrastructure of a well-designed commercial building, this separation is visible if you know what to look for. Emergency conduit is often painted red or labeled with red markings, or tagged at regular intervals with labels that identify it as emergency circuit wiring. Emergency panels, the distribution boards that serve emergency loads, are similarly marked, sometimes painted red or equipped with red trim, sometimes simply labeled clearly and consistently. The color and the labeling are not decorative, they are functional. They ensure that anyone working in the electrical infrastructure, a maintenance technician, an electrician performing modifications, an engineer evaluating the system, can immediately and unambiguously identify what is normal and what is emergency. This clarity matters especially during the moments when the system is under stress. If a fault needs to be located, if a circuit needs to be isolated, if a repair needs to be made during an active event, the ability to read the system at a glance, to know immediately which panels and which conduit pathways belong to the emergency system, can make a meaningful difference. Emergency distribution systems also reflect a careful consideration of which loads matter most and in what order they matter. Not every load in a building has the same priority. Not every piece of equipment or every circuit is equally critical to the safety and function of the building during an emergency. Life safety loads, the emergency lighting, the exit signs, the fire alarm, the smoke exhaust fans, the elevator designated for fire service, are the highest priority. These are the loads that most directly protect the lives of the people in the building. They are the first to be fed, the most carefully protected, and the last to be shed if the emergency power system is ever under capacity strain. Below life safety loads, other critical systems may also be served by the emergency distribution system depending on the building type and occupancy. In a hospital, this might include operating room power, intensive care unit equipment, and the controls for medical gas systems. In a data center, it might include server power and cooling systems. In an office building, it might include security systems, communications equipment, and the controls for critical mechanical systems. Each of these load categories may be served by its own emergency panel, its own branch of the emergency distribution system, its own connection back to the source. The architecture reflects the priorities: life safety first, then critical equipment, then lesser loads, in a way that is both logical and, when you trace it through the building, almost satisfying in its orderliness. The emergency panels themselves deserve a moment of attention because they are the most directly visible part of the emergency distribution system for anyone who has occasion to look inside an electrical room. An emergency panel looks, at first glance, much like a normal distribution panel: a metal cabinet mounted to the wall, a door that opens to reveal rows of circuit breakers, each one controlling a specific circuit, each one labeled with a description of what it serves. The panel schedule, the list of circuits and their assignments mounted inside the cabinet door, is perhaps the most informative single document in the electrical room, a compact map of what this panel feeds and where. But the emergency panel is marked differently, and it is connected differently. Its feed comes not from the normal building distribution system, but from the emergency source, through the transfer switch, from the generator or the UPS or whatever combination of sources the design specifies. Everything downstream of this panel is on emergency power when the emergency system is active. In the quiet of the night, with the building's normal power either present and supplying this panel through the normal path, or absent and supplying it through the emergency path, the panel itself looks the same either way. The breakers are in their positions, the labels are legible in the dim light. The cabinet is warm with the steady flow of current through its internal components. It is, like so much of emergency power infrastructure, a thing that reveals its importance not in its appearance, but in its function, not in how it looks, but in what it does, and in what would happen if it were not there. Consider for a moment what it would mean for a building to lack this careful architecture, to have no separation between normal and emergency circuits, to have no dedicated emergency panels, to have no clear labeling, no orderly routing, no deliberate hierarchy of loads. A power failure in such a building would be a different kind of event, not the calm, managed, nearly imperceptible transition that a well-designed emergency power system produces, but a genuine disruption, darkness in the stairwells, silence in the critical equipment rooms, no clear way to know which systems were on backup power and which were not, or where to look to restore what had been lost. The emergency distribution system, in its careful separateness and its deliberate architecture, prevents that. It ensures that the energy from the backup sources reaches exactly the loads it is meant to reach, through pathways that are protected and identifiable and reliable. It translates the abstract promise of emergency power, the generator, the batteries, the transfer switches, into concrete reality at the level of each individual circuit and each individual load. This is the last mile of emergency power, the place where stored energy and mechanical generation and carefully managed transfers become, finally, light in the corridor and power at the outlet and function in the equipment room. The place where all of the preparation and maintenance and engineering judgment that we have followed through this building comes to rest in something simple and real. A panel on a wall, a circuit in a conduit, a breaker that holds its position, a label that tells the truth about what it feeds. The building holds on, the generator runs below. The batteries sit in their racks, slightly discharged now from the first moments of the outage, being held at their present state while the generator carries the load. The emergency circuits carry their current through their red-marked conduit, through their dedicated pathways, to the panels that feed the lights and the equipment and the systems that must not stop. Everything is in its place. Everything is doing what it was designed to do, and the night is still around all of it, still and dark in the corridors where normal power has not yet returned, still and warm in the mechanical rooms where the backup systems are working, still and quiet everywhere that the emergency power infrastructure has done its job and made the disruption invisible. Rest in that stillness. The orderly rows of battery cells holding their charge, the red-marked conduit tracing its careful path through the walls, The emergency panels standing at their posts, steady and labeled and entirely prepared. The building is held. It was always going to be. All of this readiness, the warm coolant in the generator, the charged batteries in their racks, the transfer switches holding their careful positions, the fuel in the storage tank, does not arrive by accident. It is made, deliberately, repeatedly, on a schedule, by people who come to these quiet rooms not in moments of emergency, but in ordinary hours, in the course of ordinary working days, and who perform the quiet work of verification that keeps the entire system honest. This work is called maintenance and testing and inspection, and it is, in its way, one of the most important things that happens in the life of an emergency power system, more important perhaps than the emergencies themselves. Because the emergencies are rare, they arrive without announcement, and they demand readiness that was either there or was not. The maintenance is what determines which of those two things is true. Let us spend some time in the world of maintenance. It is a slow world and a careful one, and it has a rhythm to it that is, in its own particular way, deeply restful. Consider the maintenance technician arriving at the generator room on a scheduled inspection day. It is a weekday morning, perhaps, or a mid-afternoon in the middle of an ordinary week. The building above is occupied and functioning normally. The lobby has its daytime traffic. The elevators are busy. The floors are full of the quiet activity of people working at desks and in meeting rooms and in corridors, all of them drawing from the utility supply without giving it any thought at all. The maintenance technician carries a clipboard or perhaps a tablet with a checklist that has been developed over years of experience with this type of equipment in this type of installation. The checklist is not glamorous. It is thorough. It covers, item by item, the things that need to be observed and measured and verified in order to be confident that the system is in the condition it should be. The technician opens the door to the generator room and steps inside. The room is quiet, as it almost always is. The generator set rests on its base frame. The engine is not running. The alternator is still. The air has that faint, familiar quality, diesel and warm metal, and the particular stillness of a room that is designed for machinery, but is, at this moment, at rest. The technician begins at the beginning, not rushing, not skipping items, moving through the checklist in the sequence it was written, which is the sequence that makes the most sense given the layout of the room and the nature of the equipment. The first things to check are the things that should simply be present and correct. The oil level in the engine, verified through the dipstick, should be within the acceptable range, not too low, which would indicate consumption or a leak, and not too high, which can sometimes indicate a different kind of problem. The coolant level in the radiator overflow reservoir should be at its marked line. The fuel level in the base tank or the day tank should be above the minimum threshold. These checks take only a few minutes. They are simple, they are visual and tactile and immediate, but they matter because they establish the baseline, the foundation of correct conditions on which everything else depends. An engine that starts with low oil will run, but not for long and not well. An engine with insufficient coolant may overheat under sustained load. An engine with insufficient fuel may start and run for a time and then stop at precisely the wrong moment. The technician notes the readings on the clipboard. Oil, good. Coolant, good. Fuel, good. the beginning of a record that will be filed and stored and compared against previous records and used to identify trends before trends become problems. Next comes a visual inspection of the generator set itself. A slow walk around the machine, looking at it carefully, looking for anything that is different from how it was on the last inspection or how it should be. Are there any fluid leaks? A small oil seep around a gasket or a fitting might be nothing, or it might be the early sign of something that will worsen over time. Is there any corrosion on the electrical connections, the terminals of the battery, the connections at the control panel, the lugs where the output cables attach to the generator's circuit breaker? Is the exhaust system intact? The insulation on the exhaust piping undamaged, the rain cap on the exterior exhaust outlet in its correct position? Is the air intake clear? The generator needs large quantities of air to sustain combustion, and the pathway for that air, through the room's ventilation louvers, across the generator's air intake into the engine, must not be obstructed. A box stored carelessly in front of a ventilation louver, a filter that has accumulated enough dust to restrict airflow. These are small things that could become consequential things, and the inspection is the moment when they are found and corrected before they have the chance. The technician moves slowly around the machine, notes what is observed, notes what is acceptable and what requires attention. The pace of this inspection is unhurried, because the value of an inspection comes precisely from the unhurriedness of it, from the willingness to look at each thing long enough to actually see it, rather than passing over it quickly in the direction of the next item. The battery receives its own careful attention. The generator starter battery, that lead-acid cell that powers the starter motor and provides the initial energy for the start sequence, is checked for its state of charge, for the condition of its terminals, for any sign of swelling or distortion or leakage that would indicate it is aging poorly or being charged incorrectly. The charger that keeps it at full capacity is verified to be operating. The connections are checked for tightness and for corrosion. A battery terminal that has developed a layer of white or blue-white corrosion, the oxidized residue that forms around lead connections over time, can increase resistance at exactly the point where high current needs to flow freely. The starter motor draws a large surge of current in the first moments of an engine start. A corroded terminal can rob that surge of enough energy to prevent the engine from turning over at the required speed. And so the terminals are cleaned when cleaning is needed, treated with protective compound, checked and rechecked until they are in the condition that the service calls for. This attention to a single battery terminal might seem disproportionate to the scale of the overall emergency power system. The large generator, the substantial transfer switches, the rows of UPS battery cabinets nearby. But emergency power systems are chains, and chains have the well-known property of being only as strong as their weakest link. A generator that will not start because its starter battery's terminal was neglected is, in the moment it is needed, no generator at all. After the visual inspection and the fluid and battery checks, the time comes for something more active. The generator exercise. Most emergency generators are exercised on a regular schedule, weekly in many installations or monthly, depending on the requirements of the applicable code and the policies of the facility. The exercise is exactly what the word suggests: a controlled, intentional running of the generator under conditions designed to verify that it will start, that it will come up to speed, that it will produce acceptable voltage and frequency, and that it will sustain operation through the duration of the test. There are different kinds of exercises, and they serve slightly different purposes. A no-load exercise runs the generator without connecting it to any building loads. The engine starts, comes up to speed, produces its output, and that output simply runs into the generator's own controls and verification systems rather than being transferred to serve the building. No-load exercises verify that the engine starts and runs, but they do not test the full capability of the system because they do not exercise the transfer switch or verify that the generator can sustain real load. A load test, more demanding, more informative, and more satisfying in its thoroughness, connects the generator to either the actual building loads or to a portable load bank, and runs the machine under something closer to real conditions. The load bank, if used, is a device that draws a controlled and measurable amount of power from the generator, simulating the kind of demand the generator would face in an actual outage. Running under load stresses the fuel system, the cooling system, the voltage regulation, and the engine itself in ways that a no-load exercise does not. The technician initiates the exercise sequence. The start signal is sent, the engine turns. It catches that familiar deepening from mechanical churning to purposeful combustion, and builds to its operating speed. The output rises, the voltage stabilizes, the frequency settles at 60 cycles. The control panel confirms, ready, and then the generator runs. For 15 minutes or 30 or longer, depending on the protocol. The technician monitors the gauges and the control panel display, noting the oil pressure, the coolant temperature, the output voltage and frequency, the fuel consumption, everything within limits, everything as it should be. The machine doing what it was built to do, under the watchful attention of someone who knows what good performance looks like and would notice immediately if something were off. When the exercise period is complete, the generator is allowed to cool down. A brief period of running at reduced or no load before the engine is shut down, allowing the cooling system to carry excess heat away from the engine before it goes still again. Then the shutdown. The engine decelerates. The sound decreases from its steady operational note through the lower registers of deceleration and then, finally, to silence. The room is quiet again. The generator rests, and the technician notes the exercise time, the performance readings, and the result, satisfactory, on the clipboard. The emergency lighting walkthrough is a different kind of maintenance experience entirely. Where the generator room inspection is concentrated, a deep and careful examination of a single large piece of equipment in a single room, the emergency lighting inspection is distributed. It moves through the building. It takes the technician down corridors and up stairwells and through every space where emergency lighting fixtures and exit signs are installed, which in a large commercial or institutional building may be a considerable distance and a considerable number of individual devices. The technician moves through the building floor by floor, fixture by fixture, pressing the test button on each emergency lighting unit and observing whether the fixture illuminates on battery power, whether the light output appears adequate, whether the fixture holds its illumination through the minimum required test period. Exit signs are checked for illumination, for the integrity of their legend, for any indication of lamp or LED failure. This walkthrough has a particular quality of quiet thoroughness. The technician moves at a pace suited to observation rather than transit, pauses at each fixture, performs the test, notes the result, moves on. The building's corridors, empty of their daytime occupants, have a particular stillness during these inspections, the kind of stillness that makes small sounds audible and small details visible in ways that a busier building would not permit. A fixture that fails its test, that does not illuminate on battery power, or that illuminates dimly, or that goes dark before the required period has elapsed, is noted and tagged and added to the repair list. In a large building, the list may never be entirely empty. There is always something being repaired or replaced, always some fixture at some point in its maintenance cycle. But the walkthrough is what finds these things reliably and systematically before the real darkness comes. The maintenance log is, in its own way, one of the most important documents in the building. It is not a glamorous document. It is a collection of dates and readings and test results and repair records and parts replacement entries accumulated over the years of the system's operation into a detailed and honest history of how the system has behaved and how it has been cared for. It records every exercise run and every inspection finding, every battery replacement and every fuel delivery, every transfer switch test and every alarm that was investigated and resolved. The log is the memory of the system. It holds information that no individual person could carry reliably over the years that a building's emergency power system might operate. The knowledge of when the batteries were last replaced, and what capacity they tested at before replacement, and whether the charger voltage has been drifting, and when the last fuel sample came back with elevated water content, all of it written down, all of it available to whoever needs it, the next technician who comes to service the system, the engineer who is evaluating whether it needs upgrades, the inspector who is verifying that the facility is meeting its maintenance obligations. A well-kept maintenance log is a form of institutional honesty. It does not allow the system to appear better maintained than it actually is, because the record is there in the dates and the readings, telling the truth. And it does not allow deferred maintenance to accumulate unnoticed, because the log makes visible the gap between when something was last done and when it should next be done. In the quiet of the electrical room, or in the facility management office where the binders of inspection records are kept on a shelf, the maintenance log holds its patient record. Page after page of ordinary dates and ordinary readings, representing year after year of ordinary care for a system that will, when the extraordinary moment arrives, be ready because of all those ordinary hours. This is the rhythm of maintenance, not dramatic, not urgent, not performed under any particular pressure or in response to any particular alarm, simply recurring on its schedule in the background of everything else the building does. The technician who exercises the generator on a Tuesday morning and notes the satisfactory readings on the clipboard does not know whether the generator will be needed that afternoon or not for years. The person who walks the corridors testing emergency lighting on a Thursday does not know whether the lights will be called upon that evening or not until next spring. The maintenance is performed not in response to anticipated need, but in preparation for possible need, and the two things are entirely different in their demands on the person performing the work. Anticipated need creates urgency, possible need creates discipline, and discipline sustained over months and years and the full operational life of the system, is what readiness actually is. Not a state that exists at a single moment, but a condition that is rebuilt and re-verified and maintained continuously by the patient, recurring work of people who understand that the value of what they are doing will only be proven in a moment that has not yet arrived. The generator room waits, the battery room waits, the transfer switch cabinets hold their positions, and somewhere in the building, on a shelf or in a drawer or in a digital record system, the maintenance log holds its honest record of everything that has been done to keep the waiting worthwhile. The systems are ready, the work is done, and the building, tonight and every night, is held by the accumulation of all those quiet Tuesday mornings and Thursday afternoons and scheduled exercise runs and corridor walkthroughs that no one will ever think to celebrate. Rest in that. The clipboard notes, the satisfactory readings, the orderly, patient record of care given to systems that will never say thank you and will never need to. The work was its own reward. The readiness is the proof. Everything we have followed tonight, the monitoring systems and the transfer switches, the generators and the UPS cabinets, the battery rooms, and the carefully separated distribution pathways, all of it comes into sharpest focus in a particular kind of building. Not the office building we began with, quiet and empty at this hour. Its emergencies more matters of inconvenience than of consequence. Not the data center, though its dependencies on continuous power are real and significant, but the hospital. The hospital is where emergency power becomes something more than infrastructure, where it becomes, in the most literal sense, a condition of continued life, where the question of whether the backup systems will work, whether they will transfer in time, whether the generator will start, whether the circuits will hold, is not an abstract engineering question but a deeply human one, with answers that can matter to specific people in specific rooms on any given night. And so let us leave the building we have been imagining and travel now to a different kind of place. Let us walk slowly and quietly into a hospital at night. The hospital at night has a quality all its own. It is never entirely still in the way that an empty office building is still. There are always people present, patients in their beds, nurses moving through corridors on their rounds, physicians responding to calls, technicians monitoring equipment in rooms that never close. The hospital does not have an off state. It does not empty out and wait for morning. It continues through every hour of the night at a pace that is quieter than the day, but never fully at rest. The corridors at this hour have a particular light, different from the bright, even fluorescence of the daytime. Many hospitals dim the corridor lighting at night, creating a softer environment that is less disorienting for patients who might be moved through the hallways, less harsh for the staff who work the long overnight shifts. The light is still sufficient, still clinical, but it has a gentleness to it that the daytime does not always permit. In the patient rooms, low night lights glow near the floor. Monitoring equipment beside each bed traces its quiet patterns of light, the slow peaks and valleys of a cardiac waveform, the steady numerals of an oxygen saturation reading, the gentle rhythmic display of a ventilator cycling through its programmed breaths. These machines work without interruption. They have been working since the patient was connected to them, and they will continue working through the night. And the question of whether they will continue working is not one that the patient or the nurse attending them should ever have to hold in their minds. That question belongs to the emergency power system. The principles we have followed in the commercial building, the monitoring, the transfer, the generation, the distribution, are all present in the hospital. But in the hospital, they are present in a more structured, more layered, more rigorously defined form, because the consequences of failure in a hospital are not the same as the consequences of failure in an office building. The design of the backup power system is held to a correspondingly higher standard. The framework that governs hospital emergency power systems in the United States and in much of the world in similar forms divides the emergency electrical system into branches, not a single emergency system that serves everything critical, but several distinct branches, each with its own defined scope, each with its own transfer switch and its own pathway from the emergency source, each designed to serve a specific category of load with a specific level of reliability and priority. This branching structure is the architecture of the hospital's emergency power system, and understanding it, feeling your way through it slowly, room by room and branch by branch, is a way of understanding what the hospital is protecting and why. The first and most fundamental branch is the life safety branch. The life safety branch exists for one purpose above all others: to ensure that in any emergency, a fire, a power failure, a mass casualty event, any disruption that might require the movement of people through the building or the response of emergency services, the physical environment of the hospital remains navigable and safe. This means the exit signs are lit, the corridor emergency lighting is on, the lighting in the stairs and the exit pathways is active, the fire alarm and detection system is powered. The systems that control smoke barriers and fire doors and smoke exhaust, the mechanical means by which the hospital manages the movement of smoke through its spaces in the event of a fire, these systems are energized and functional. The life safety branch is transferred to emergency power as quickly as the code requires, typically within 10 seconds of utility failure for hospitals, the same standard that applies to life safety systems in other building types. It is the branch that arrives first, that is most tightly time-constrained, that carries the loads on which physical safety most directly depends. And it is kept separate, not just from the normal power system, but from the other emergency branches as well. A fault on one branch must not propagate to another. The failure of a circuit-feeding patient care equipment must not reach across and extinguish the exit signs. The separation that we followed in the commercial building's emergency distribution system is present here in a more elaborate and more carefully specified form. Alongside the life safety branch, the hospital's emergency system includes a critical branch. The critical branch serves the equipment and the spaces where patient care is most intensive. Operating rooms, intensive care units, the recovery room, labor and delivery suites, the areas where patients are at their most vulnerable, where the monitoring and intervention equipment that sustains them is most essential, where any interruption in power could have immediate and direct consequences for clinical outcomes. In an operating room at night, perhaps being used for an emergency procedure, perhaps simply in standby for the cases that will begin tomorrow morning, the critical branch feeds the surgical lighting, the anesthesia machine, the patient monitoring equipment, the electrosurgical units, the infusion pumps, all of it connected, all of it sustained, all of it drawing from circuits that are on the critical branch and therefore on emergency power when the normal supply is lost. The critical branch also transfers within 10 seconds. This is not because 10 seconds is imperceptible. It is long enough to notice, long enough for monitoring equipment to alarm, long enough for a moment of genuine concern in a clinical environment. It is because 10 seconds is the standard that has been determined, through long experience and careful analysis, to be the limit within which the most critical clinical functions can be sustained by other means, by the UPS systems and battery-backed devices that bridge the gap, by the clinical skills of the staff present, by the inherent resilience of well-designed medical equipment, while the generator completes its startup. In the operating room, the surgeon and the anesthesiologist do not stop working when the power flickers and the backup lighting comes on and the monitoring equipment resets momentarily before returning to its steady display. They have been trained for this. The protocols exist. The UPS behind the anesthesia workstation has held the waveform through the transition. The overhead surgical light fed by the critical branch is back on within seconds. The procedure continues. This is the hospital's emergency power system doing exactly what it was designed to do, making the disruption brief enough and managed enough that clinical care can continue through it with minimal interruption. There is a third element of the hospital's emergency electrical system, broader than the critical branch and the life safety branch, that encompasses the equipment and functions that are essential to the hospital's operation as a whole, but that are not immediately life-threatening if they experience a slightly longer transfer time. This portion of the system, sometimes called the equipment system, encompassing heating and ventilation for patient spaces, medical gas controls, nurse call systems, certain laboratory and pharmacy equipment, and other functions that are critical to ongoing operations, even if not to immediate survival, is also transferred to emergency power, but with a somewhat more relaxed timeline. Not within 10 seconds, but within a defined period that still ensures continuity of hospital function across the full scope of an extended outage. Together, these elements form the essential electrical system of the hospital: life safety, critical, equipment. 3 distinct pathways, each with its own transfer switch and its own circuits and its own carefully defined scope, all fed ultimately from the same emergency generator or generators, all designed to work together to keep the hospital whole and functional when the utility supply is gone. The generator plant of a large hospital is a different scale of installation from what we imagined earlier in the commercial building. A large acute care hospital, the kind with hundreds of beds, multiple operating suites, an active emergency department, imaging equipment, and the full spectrum of clinical services, may have not one emergency generator but several. 2 or 3 or more large units arranged in a configuration that provides redundancy not just against utility failure but against the possibility of any single generator failing to start or failing during operation. Because the hospital's emergency power system must continue to function even if something goes wrong with one of the backup sources themselves. The single point of failure that is acceptable in a less critical building is not acceptable here. If one generator fails to start, another must be ready to take over. If one transfer switch develops a fault, the loads it serves must have an alternate path to power. Redundancy is layered into the hospital's emergency power design in a way that reflects the seriousness of what the system is protecting. The generator room of a large hospital, therefore, may be a substantial space, a purpose-built structure, sometimes located in the basement of the main building, sometimes in a separate generator building on the hospital campus, with room for multiple large generator sets and all their associated fuel, cooling, exhaust, and control systems. It is a warm and mechanical space, full of the careful engineering of systems that are expected to be available at any moment for any duration without advance notice. These generators are exercised regularly. The exercise schedules for hospital generators are not casual. They are documented, verified, and in many jurisdictions inspected by authorities having jurisdiction who want to confirm that the system is genuinely ready, not merely apparently ready. The exercises run under load. The transfer sequences are tested. The runtime and performance data are recorded, and the results go into maintenance logs that represent over time a detailed history of the system's reliability and readiness. There is another dimension of hospital emergency power that deserves quiet attention, and it is one that speaks to a quality of care in system design that goes beyond the purely technical. In a hospital, patients are aware, to varying degrees, in varying states of consciousness and clarity, of the environment around them. A patient lying in a bed in a quiet room at 2 a.m, attached to a monitoring device and waiting for sleep, is sensitive to changes in their environment in ways that a healthy person in a busy office building is not. The sound of an alarm, the sudden extinguishing of a nightlight, the brief flicker of the monitoring display, these events register differently in that context. They can cause anxiety. They can disrupt rest that is already fragile. They can produce questions and concerns that compound the stress of being in a hospital at all. The emergency power system of a well-designed hospital takes this into account. The goal is not merely that critical equipment keep running, though that is the essential goal, but that the transition from utility to emergency power be, from the patient's perspective, as imperceptible as possible, that the monitoring equipment does not alarm unnecessarily, that the corridor outside the room does not go dark before the backup lighting activates, that the sounds and lights of the clinical environment remain as steady and as reassuring as they are expected to be. This is a high standard. It requires the UPS systems behind the most sensitive equipment to hold through the transfer without missing a beat. It requires the transfer switches to act within their specified times. It requires the generator to start reliably and quickly. It requires the entire system to function not merely adequately, but smoothly enough that a patient lying half awake at 2 a.m. might not even register that anything changed. A good hospital power system is measured in the end not by how often it is noticed, but by how completely it prevents disruption. The absence of awareness is the proof of success. Walk now through the hospital at night with this understanding in place. The nurse moving down the dimly lit corridor, making her rounds, glancing through the windows of patient rooms to check that monitoring equipment is tracing its steady patterns. She is moving through a space held in quiet readiness by all the systems we have followed. The transfer switches in their rooms, the generators on standby in their plant, the UPS cabinets behind the most sensitive equipment, the battery-backed lighting in the corridors and the stairwells, the red-marked emergency conduit running through the walls beside her, carrying circuits that are separated and protected and ready. She does not think about any of this. She should not have to. The system is doing its job by not requiring her attention, by being present without being intrusive, by protecting the environment she works in with a completeness that is invisible precisely because it is effective. In the patient rooms, the monitors continue their quiet tracing, the ventilators cycle through their programmed sequences, the infusion pumps deliver their measured doses, the nightlights glow near the floors. Everything is as it should be, as it has been all night, as it will continue to be. And somewhere below, in the warm mechanical rooms of the hospital's lower levels, the generators rest on standby with their coolant warm and their starters charged and their fuel tanks full. The transfer switches hold their positions in their cabinets. The battery systems maintain their charge. The monitoring circuits watch the utility supply with their patient, continuous attention. The hospital is, in the fullest sense, prepared. Not dramatically, not visibly, not in any way that announces itself or asks to be acknowledged, but completely and carefully and with a depth of planning and maintenance and engineering attention that reflects the seriousness of what it is asked to protect. The night in the hospital moves gently on. A cart wheels quietly down a corridor. A monitor alarm sounds briefly and is silenced by a nurse who recognizes it as minor, as expected, as nothing requiring concern. The building breathes in its slow institutional way, the ventilation system cycling, the heating maintaining its set points, the elevators resting on their home floors in the small hours before morning activity begins again. And through all of it, the emergency power system watches, holds, waits, ready to act within seconds if the utility supply falters, ready to sustain the hospital through whatever duration the outage requires, ready to keep the environment steady and lit and powered so that the work of care can continue without interruption. This is what emergency power is for, stated in its most complete form. Not for offices or data centers or commercial buildings, though it serves all of those faithfully and well, but for this, for the place where the stakes are highest, and the margin for error is smallest, and the need for quiet, reliable, invisible continuity is most deeply felt. The hospital holds, the systems hold, and the night passes gently as it was always meant to. There is one more room to visit tonight. We have moved through many spaces in this long, quiet journey. The monitoring rooms and the transfer switch cabinets, the generator plant and the UPS enclosures, the battery rooms and the electrical panels, the hospital corridors and the patient rooms with their softly glowing monitors. We have followed power from its source to its destinations, traced circuits through conduit and panels and breakers, watched transfer switches make their careful selections and generators wake from their long standby sleep. But there is a question we have not yet answered fully, a question that sits patiently at the base of everything the generator does and everything the emergency system promises. The generator runs on fuel, and the fuel has to come from somewhere. Where it comes from, how it is stored, how it is maintained, how it is delivered to the engine at the moment the engine needs it, is the domain of the fuel system. And the fuel system, like every other element of emergency power infrastructure, has its own quiet rooms and its own patient machinery and its own particular form of readiness that it holds through all the hours when nothing is required of it. Let us go there now, slowly, without hurrying. In most commercial and institutional emergency power installations, the fuel that sustains the generator through an outage is diesel. Diesel fuel is the standard for this application for reasons that are practical and well established. It is stable enough to store for extended periods. It is energy-dense enough to allow meaningful runtime from tanks of manageable size, and the diesel engine is a proven technology with a long and reliable history in standby power applications. When you imagine a generator room, the smell you might associate with it, that faint particular scent of petroleum that hangs in the air even when the engine is not running, is mostly the smell of diesel, the fuel in the lines, the residue on the fittings, the trace of the last exercise run that settled into the room and never quite left. The fuel system begins at the storage tank. In smaller installations, this might be a base tank, a tank built directly into the frame of the generator set, sitting beneath the engine and the alternator, holding enough fuel for several hours of runtime at full load. In larger installations and in facilities that require longer guaranteed runtimes, the fuel is stored in a separate, dedicated tank, sometimes located adjacent to the generator room, sometimes in an underground tank below the building's grounds, sometimes in an above-ground tank in a protected enclosure outside. The size of the tank is not arbitrary, it is calculated. The design process considers the generator's expected fuel consumption at its rated load, the minimum runtime required by code or by the facility's own operational needs, and the margin that prudent planning adds beyond the minimum. A hospital generator, for instance, may be required to demonstrate a certain number of hours of runtime capability, and the fuel tank must be sized to support that runtime fully, not approximately, not almost, but completely and with room to spare. From the storage tank, fuel travels to the engine through a supply system that is as carefully designed as any other part of the installation. There are fuel lines, typically steel or flexible metal, sized to deliver the flow rate the engine demands at full load without restriction or pressure drop. There are filters positioned in the supply path to remove particulates and water that might otherwise reach the engine's injection system and cause problems. There are day tanks in some installations, smaller tanks located close to the engine that maintain a local reserve of fuel, ensuring that even if the supply from the main tank is briefly interrupted, the engine has immediate access to what it needs to keep running. And there are controls, fuel level monitoring that tracks the contents of the storage tank and reports that level to the building management system or the generator's own control panel. Low fuel alarms that trigger when the level drops below a defined threshold, signaling that a fuel delivery needs to be arranged before the reserve runs out. Transfer pumps that move fuel from the main storage tank to the day tank when the day tank's level drops, automatically and without manual intervention, keeping the local supply maintained throughout a long outage. All of this, the tanks and the lines and the filters and the pumps and the level sensors and the alarms, works together to ensure that the engine has what it needs for as long as it needs it, seamlessly, in the background, without the generator room staff or the facilities team needing to manage it manually in the middle of an emergency, when they have other things to attend to. Fuel quality deserves its own quiet moment of attention because it is one of the less obvious and more consequential dimensions of fuel system maintenance. Diesel fuel does not last forever. Left in a tank for an extended period, it begins to change. Oxidation occurs. Microbial growth, certain species of bacteria and fungi that thrive at the interface between diesel fuel and water, can develop in tanks where water has accumulated. Sediment forms and settles. The fuel becomes darker, cloudier, more viscous than it should be. And fuel in this condition does not serve the generator well. It can clog filters, it can foul injectors, it can cause the engine to run rough or to fail to start cleanly at the critical moment when clean starting matters most. This is why fuel management is a real and recurring part of emergency power maintenance. Fuel is sampled on a schedule, drawn from the tank and tested for clarity, water content, microbial contamination, and other indicators of degradation. Fuel polishing systems, recirculating filtration equipment that draws fuel from the tank, passes it through fine filters, and returns it cleaned and clarified, are used in some installations to maintain fuel quality continuously rather than simply monitoring it and reacting. Fuel stabilizing additives are used in others. The goal of all of this is the same. When the engine starts, when the signal comes at 2 in the morning or 2 in the afternoon or any other moment when no one anticipated needing the generator, the fuel flowing from the tank to the injectors should be clean and consistent and exactly what the engine was designed to consume. Not degraded, not contaminated, not a source of hesitation in a moment when hesitation is not acceptable. Good fuel planning feels invisible until the moment it prevents a problem. It is one of those maintenance disciplines that, when it is working well, produces no visible evidence that it is working at all. The generator starts cleanly. The engine runs smoothly. The output is steady, and nobody in the building above ever knows that the quality of the fuel in the tank had anything to do with it. Fuel delivery is the final piece of the fuel system picture, and it is worth acknowledging because it represents the point where the emergency power system's readiness extends beyond the building itself and into the relationship between the facility and the world outside it. A fuel tank, however large, holds a finite supply. For a short outage, a few hours, perhaps half a day, the on-site storage is typically more than sufficient. But for a long outage, the kind that follows a major storm or a widespread grid failure, or any event that disrupts the utility supply for days rather than hours, the fuel in the tank will eventually run low. And so, facilities with serious emergency power commitments maintain relationships with fuel suppliers. They have delivery contracts in place. They have contact information current and accessible. In some cases, they have priority delivery agreements that ensure their facility is served before lower priority customers in the event of a region-wide emergency when fuel demand surges and supply is constrained. The fuel delivery arrangement is, in a sense, the part of emergency power planning that acknowledges the limits of what can be prepared in advance. No tank is infinite. No on-site reserve can last forever. At some point, the building's connection to the outside world, its supply chains, its vendor relationships, its place in the broader logistics of emergency response, becomes part of what determines whether the generator can keep running. And so the maintenance logs that hold the test records and the battery inspection results and the fuel quality samples also hold the vendor contacts and the delivery schedules and the confirmation that the supply arrangements are current and reliable. All of it part of the same discipline, all of it directed toward the same end. Let us rest now with the full picture of everything we have followed tonight. Not to summarize it briskly, but to hold it gently, the way you might hold the memory of a place you have spent time in, turning it slowly in your mind before setting it aside for sleep. There is a building somewhere in your city tonight, perhaps many buildings, perhaps the hospital a few miles from where you are lying right now, or the office tower downtown, or the data center on the edge of the industrial district with its rows of humming servers and its carefully climate-controlled floors. These buildings are quiet. Most of them are dark, or nearly dark, in the way that buildings are dark when the people who fill them during the day have gone home for the night. The parking lots are empty, or nearly so. The lobbies are lit by a single lamp at the security desk. The elevators are resting, and yet none of these buildings are unprotected. In each of them, somewhere in the lower levels, or in a dedicated plant room, or in a structure built alongside the main building for exactly this purpose, a generator is resting on standby. Its engine is warm. Its starter battery is fully charged, maintained at exactly the state of charge it needs by a small, quiet charger that has been working steadily for days or weeks without anyone noticing it. Its fuel tank is full, or close to full, with clean and tested diesel ready to flow the moment the engine asks for it. Nearby, or in the same room, a transfer switch is holding its position. Its contacts are connecting the building's emergency circuits to the normal source, as they have been all day and all evening and all night. The contacts are not strained. They are not warm. They are simply present, mechanically certain, doing the ordinary work of holding a position that requires no effort to maintain, but that is ready to change in an instant if the signal arrives. Further along the electrical rooms, battery systems are sitting in their racks and their cabinets, holding their charge with the patient completeness of things that have nothing to do but wait. The chargers are doing their slow, continuous work. The cells are at capacity. The stored energy is present and available, ready to flow at the first sign that the normal supply has been interrupted. And throughout the building, above all of this, the monitoring system is watching the incoming utility supply with its continuous, undramatic attention, measuring the voltage, confirming the frequency, verifying the phases, comparing what it sees against what it expects to see, and finding, at this moment, no discrepancy. Everything is as it should be. The utility is healthy. The building is receiving its normal supply. Nothing is required. The monitoring system notes this and continues watching. This is the nighttime state of emergency power systems everywhere. Not active, not responding, not in the middle of any sequence or transition, simply present, simply watching, simply maintained and charged and fueled and ready. It is easy from the outside to forget that all of this exists, to walk through a building during the day in the flow of ordinary activity and never once think about the generator room or the transfer switch cabinet or the battery room or the fuel tank, to use the lights and the elevators and the computers and the climate control and simply receive, without reflection, the continuous service that a powered building provides. But the infrastructure is there. It was there before you arrived, and it will be there after you leave. And it holds its readiness through every hour of every day without asking for acknowledgement and without requiring appreciation. There is something genuinely comforting in this if you allow yourself to feel it. The world around you at night is full of systems like these, full of machinery and electronics and infrastructure that is quietly, reliably, continuously doing its work in the background of the life you live. Emergency power systems are one part of that background, one layer of the deep, invisible architecture of reliability that makes modern buildings possible and modern life continuous. And all of it is held tonight by people who planned it and installed it and test it and maintain it. Engineers who spent careful hours designing the separation of circuits and the sizing of generators and the arrangement of transfer switches. Technicians who climb into generator rooms on scheduled maintenance days and check the oil and test the batteries and sample the fuel and record the results in logs that will tell the truth about whether the system is ready. Facilities managers who review those logs and order replacement batteries when the capacity tests show diminishing returns and arrange fuel deliveries before the tank drops too low. This work is quiet, it is not glamorous, it does not often attract attention, but it is real, and it is ongoing, and it is the reason that a hospital patient can sleep through the night without the monitoring equipment beside her bed ever going dark. The night is deep now. Whatever hour it was when we began this long, slow journey through the emergency power systems of commercial buildings, more of the night has passed since then. The city outside is quieter than it was. The traffic sounds, if there were any, have faded. The building you are in is at its most still, and somewhere in the electrical rooms and the generator plants and the battery cabinets of buildings near and far, the systems are doing what they have been doing all night, watching, holding, waiting, not anxiously, not urgently, not with any of the tension that the word waiting sometimes carries. They wait the way a well-made thing waits, with the ease of a system that knows what it is, that has been built and maintained for exactly its purpose, that requires nothing more of itself than to be present and ready for as long as it is needed. The exit signs glow their steady red and green in the empty corridors. The generator coolant holds its temperature. The battery chargers tick along at their trickle rates. The monitoring circuits measure and confirm and measure again, finding everything acceptable, finding everything as it should be, finding nothing that requires a response. And the night continues. You are, right now, somewhere in the world that is held by systems very much like these. The building around you, wherever you are, whatever it is, has infrastructure behind its walls and beneath its floors that is sustaining the environment you are resting in, keeping the temperature stable, maintaining the circuits that keep your devices charged, watching the incoming power with quiet, continuous attention. You do not need to think about any of it. That is the deepest gift of good infrastructure, not that it works, though it does, not that it is reliable, though it is, but that it asks nothing of you. It simply holds, so that you do not have to. Let it hold now. Let the generator rest on its warm standby in whatever plant room it occupies tonight, its engine still, its fuel full, its starter ready. Let the transfer switch hold its contacts in their patient position, watching for a signal that may not come until long after you have woken and gone about your day and come back again to rest. Let the batteries sit in their quiet rows, charged and waiting, holding their stored energy with a stillness that asks nothing and promises everything. Let the monitoring system do its watching. Let the emergency circuits run their separated pathways through the walls. Let the exit signs glow in the corridors you are not walking through tonight. Let all of it continue as it was designed to continue in the background of your rest. The building is held, the systems are awake so that you do not have to be, and the night is long and quiet and entirely safe. Sleep now. The night has grown very deep now. Whatever sounds were present at the beginning of this long, slow journey, the distant hum of traffic, the occasional sound of wind against the building, the small ambient noises of a world that had not yet fully settled into its nighttime stillness. Those sounds have faded or softened, or been replaced by the deeper quiet that only arrives in the small hours, when the night is at its most complete. You have followed for a long while now the hidden systems of buildings, the monitoring circuits and the transfer switches, the generators and the batteries, the carefully separated distribution pathways, and the soft glow of emergency lighting in empty corridors. You have traveled through electrical rooms and generator plants and hospital hallways and battery rooms and stairwells lit by the patient amber of emergency fixtures. You have learned something real, something true about the world of buildings and the infrastructure that holds them. And that knowledge can rest in you now, quietly, without needing to be rehearsed or reviewed. It is simply there, the way all the things we absorb in gentle hours are simply there, present without pressure, held without effort. There's nothing more to follow now. No new rooms to enter, no new systems to trace. Only the night, and the buildings in it, and the quiet work that continues without any need for your attention. Imagine, if you like, a view from a very great height. Not so high that the buildings below are invisible, but high enough that you can see many of them at once. A city at night spread across a valley or a plain or a stretch of coastline, its lights creating the familiar scatter of illumination that cities produce in the dark. Streets and intersections marked by streetlights. Buildings lit at their edges and their entrances. The occasional brightness of a building where some activity continues through the night. From this height, the individual buildings are shapes, rectangles and towers, and the sprawling low profiles of hospitals and industrial facilities and campuses. Each one dark in most of its windows, each one holding its contents, its equipment and its infrastructure, and in some of them the people who live or work or receive care within them, in the way that buildings hold things, steadily, without visible effort, simply by being what they are. And in each of them, invisible from this height, the emergency power infrastructure is present, the generators on their base frames, the transfer switches in their cabinets, the batteries in their rows, the monitoring circuits doing their patient watching, all of it duplicated, multiplied across the hundreds and thousands of buildings in the view below, a vast invisible network of readiness distributed across the city, held in every structure that has been designed with the understanding that the utility supply, however reliable, is not guaranteed. The city does not know it is protected in this way. The city simply rests. Come down now from that height. Down through the cool night air, past the upper floors of the towers with their few illuminated windows, past the rooftop mechanical equipment and the red aviation warning lights blinking their slow, patient rhythm at the building's highest points, down to the street level and then below it, into the basements and the mechanical levels where the systems live. Choose any building. An office tower, perhaps, in the center of a city block, its lobby dark except for the security desk lamp and the glow of the guard's monitor. Step through the service entrance on the north side of the ground floor, down the corridor that smells of concrete and electrical insulation, through the heavy door marked Electrical Room, authorized personnel only, and into the space that has been present in our imagination throughout this long night, The main switchboard stands near the center of the room. Its painted steel cabinet is warm to the touch, carrying within it the steady current that the building draws from the utility supply even in these quiet hours, the base load of the building, the minimum demand of a structure at rest. Security systems, stairwell lighting, the elevator control circuits waiting for a call that will not come until morning. The mechanical system controls maintaining temperature set points in empty floors, all of it drawing quietly, continuously from the grid. The monitoring equipment is here, in this room, doing its watching. The incoming utility supply is healthy tonight. The voltage is within its acceptable range. The frequency is steady at 60 cycles. All three phases are present and balanced. The monitoring system notes this, as it has been noting it every moment since it was last tested, and continues its patient observation without comment. On the far wall, the transfer switch cabinet stands in its position. The indicator light for the normal source is green. The emergency source indicator is dark. The generator is not running. The emergency source is not active. Everything is as it should be in a building receiving reliable utility power. The transfer switch contacts are in their normal position, connecting the emergency distribution panels to the utility-fed normal source. Holding, steady, untroubled, move deeper into the building, through a second door and down a short corridor to the generator room. The room is still. The generator set occupies its corner of the space, large and dark and composed on its base frame. The engine is cool, not cold, because the block heater is working, maintaining the coolant at a temperature that will allow fast starting but cool in the sense of being at rest, of holding the particular stillness of machinery that is not running and has not recently run. The fuel gauge on the generator's control panel shows the tank at a comfortable level. The last fuel delivery was recent. The last exercise run produced satisfactory readings that are now recorded in the maintenance log, which sits in its binder on the shelf near the door. The oil is clean and at the correct level. The coolant is at its mark. The starter battery is fully charged. Its terminals clean, its charger showing the green light of a completed charge maintained at float. Everything in this room is at rest, and everything in this room is ready. These two things coexist here without any tension. The rest is not opposed to the readiness. It is an expression of it. A system that is truly prepared does not need to be in motion to demonstrate its preparation. It simply holds what it holds, maintains what it maintains, and waits with the ease of something that knows exactly what it is for. The room is warm from the block heater's work. The air is still. The faint smell of diesel is present, as it always is. And outside the ventilation louvers, the night air moves softly past, carrying the distant sounds of the city at rest. Upstairs now, up through the building, floor by floor. Each floor is dark. The workstations and the monitors and the task lighting of the daytime are off. The conference rooms are empty. The chairs arranged around the tables in the way that no one will deliberately arrange them during the workday, but that they settle into when left alone overnight. The small kitchen on the 7th floor has its coffee machine dark and its refrigerator humming its small domestic hum, the only sound on the entire floor. In the corridors, at intervals, the emergency lighting fixtures are present. During the day, when normal lighting fills the building, these fixtures are easy to overlook. They blend into the ceiling or mount quietly on the walls and carry no particular visual weight. But at night, when the corridors are otherwise dark, the emergency fixtures and the exit signs become the primary illumination. Their light is low and even and clear. The corridors are readable. The exit doors are marked. The stairwells at either end of each floor are accessible and lit. The building is dark in all the ways it is supposed to be dark at this hour, and lit in all the ways it is supposed to be lit. The absence of normal lighting is not a problem to be solved. It is simply the nighttime state of a building at rest. And the emergency lighting that remains active is not a response to emergency. It is simply always on, always present, marking the pathways that would matter in a moment of disruption with the same steady patience that it applies to all the hours when no disruption occurs. Now move in your mind across the city, from this office tower to another building, a few blocks distant, a building you might pass on any ordinary morning without giving it a second thought. Perhaps it is a mid-rise residential building with a few commercial floors at the base. Perhaps it is a government building, its facade familiar and slightly imposing in the daytime, simply dark and quiet now. Perhaps it is a hotel, with a handful of rooms still lit in the upper floors where guests are awake, but most of its mass dark and still. Each of these buildings has its own version of everything we have explored tonight, its own electrical room, its own monitoring circuits, its own transfer switch or switches, its own generator if it is large enough and its occupancy requires one, its own emergency lighting fixtures marking its corridors and stairwells. Each one designed and installed and maintained according to the same fundamental principles, the same separation of normal and emergency circuits, the same automatic response to utility failure, the same layering of protection that ensures the most critical functions survive whatever disruption the night might bring. The details differ, the scale differs, the specific equipment differs, but the intention is the same everywhere. The building should be prepared. The people inside it should be protected. The systems should be capable of responding without waiting for anyone to notice that a response is needed. And so they are. Quietly, in building after building across the city, the systems are present and ready. The monitoring circuits watch. The transfer switches hold. The generators rest with their coolant warm and their fuel at level. The battery chargers maintain their trickle. The emergency lighting traces its soft paths through the dark corridors. Come to rest now, wherever you are resting tonight. The room you are in is part of a building. That building has walls and a roof and a foundation, and within those walls runs the infrastructure that sustains the environment you are in. Electrical circuits carrying current to the outlets and the fixtures and the systems that make the building function. Mechanical systems maintaining the temperature. The ambient, invisible work of a structure that is doing its job without requiring anything of you. And somewhere in that building, or in a building very nearby, there are systems that belong to the same family as everything we have spent this night exploring. Maybe a generator, maybe a transfer switch, certainly some form of emergency lighting, the exit sign above the door you came in through, glowing steadily in whatever color your local code requires, illuminating nothing in particular at this moment and illuminating exactly what matters if it is ever needed. These systems are awake. You are not required to be. The night in its deepest hours has a quality that is different from the night at its beginning. Earlier in the evening there is still the residue of the day, the energy of activity recently concluded, the awareness of the transition from one state to another. But in the deep night, that residue is gone. What remains is simply the night itself, and the stillness, and the long, even quality of hours that pass without effort or incident. This is the hour that emergency power systems are most quietly at home in. Not because they are more likely to be needed, outages have no preference for the hour, but because the deep night is when the quality of standby readiness is most purely itself. The building is at its most still and the systems are at their most patient, and the relationship between the two, the quiet building and its quiet protectors, is at its most complete. The monitoring circuit watches the utility supply and finds it acceptable, as it has found it acceptable for all the hours since it was last tested, and will continue to find it acceptable through all the remaining hours of this night. The transfer switch holds its normal source position without strain, its contacts cool, its controls resting in the state they were designed to rest in when nothing is required of them. The generator sits in its room with the ease of a well-maintained machine that has been asked nothing tonight and is prepared for anything. None of these systems are impatient. None of them are restless. They do not experience the night as long. They simply continue, in the way that purpose-built things continue when they are doing what they were made to do, without friction, without resistance, without any of the effort that continuity sometimes costs. Let the thought of them settle in you now, the way thoughts settle when the body is still and the mind is drifting, and the line between waking and sleeping has grown soft and indistinct. The generators, the batteries, the transfer switches, the monitoring circuits, the fuel in the tanks, the maintenance logs on the shelves, the emergency fixtures in the corridors, the exit signs above the doors, all of it present, all of it held, all of it continuing through the night in the quiet, reliable, invisible way that the best systems continue, without drama, without announcement, without any need for acknowledgement from the people they protect. You are one of those people tonight. The building around you is holding you in the way that buildings hold people, with the accumulated solidity of its walls and its systems, with the continuous work of its infrastructure, with the quiet readiness of everything that has been designed and installed and maintained so that your rest can be untroubled. You are not responsible for any of it tonight. You are simply inside it, simply resting within the shell of a protected space in a building that knows what to do if something changes, and that will do it without waking you. The monitoring circuit watches, the transfer switch holds, the generator rests warm and ready in its quiet room. The batteries carry their charge through the night. The emergency lighting marks the corridors with its steady, patient glow, and somewhere in the maintenance log, on a shelf or in a drawer or in a record system, the dates of the last inspections are written down in someone's careful handwriting, confirming that all of this readiness is real and measured and verified and current. The night passes slowly, evenly, without incident. The systems continue, the building holds, and you are resting safely within all of it, within the invisible architecture of preparation and care that surrounds you without asking to be noticed, that protects you without asking to be thanked. that continues its quiet work through every hour of the dark so that the morning, when it comes, finds everything exactly as it should be. Let the night be long. Let the systems do their watching. Let the darkness be gentle and the stillness be deep, and the hours pass without weight or urgency or any demand at all. You are held. Sleep now.